and welcome back to this section of the course. We are going to look at finding derivatives of trigonometric functions such as cosec of x, sec of x, cotan, and arc sine of x, or cosine of x. So, for those who find this intimidating, arc sine of x is nothing but the inverse sine of x. For well, then arc cosine is inverse cos of x. Arc tan is nothing but inverse tan of x. So let's get to the core of this lecture. So looking at cosec of x, we know that cosec is 1 over sine. So we can rewrite uh, y as 1 over sine of x, and we can rewrite that again as sine of x to the power of minus 1. So using the power rule and the chain rule, we know that the power will come at the front and we have to subtract 1 from the minus 1. So we'll have negative sine of x to the power minus 2 multiplied by the derivative of inside. The derivative of sine is cos, so we'll have that cos multiplied. So at the minute, it's a linear expression here, but we can put negative powers in the denominator and write sine x to the power of positive 2, so that it will look something like so, with the negative sign still hanging at the front. So we can tidy things up even further. We can expand, and rather than having that sine square, we can write that sine of x multiplied by sine of x. So because we know that cos of x over sine of x might give us another trigonometric expression, which is, we can rewrite this expression as the first term on the left is 1 over sine of x, which we can write as cosec of x, and cos over sine is 1 over tan, which is cotan of x. So, and there is a negative sign at the front, so the final derivative will be negative cosec multiplied by cotan of x. Okay, so let's look at example number 2. What's the derivative of secant of x? So we know that secant is 1 over cos, and we can rewrite 1 over cos as cos to the power minus 1, using the same trick that we used in the last example. We're going to use the chain rule, and the chain rule says that we need to multiply this negative cos of x to the power minus 2 by the derivative of cos itself, which is another minus sign. So these two negatives, when multiplied with each other, cancel away, and we can rewrite that cos of x as cos of x times cos of x square is cos of x times cos of x in the denominator, and this expression simplifies to secant times tan. So there is another form. Find these formulas. I'm putting them on top of the page here, but you can find them in your formula booklet as well. But you may be asked to prove these. Uh, why is it that the derivative is as such? So you need to know the proof as well. So cotan is 1 over tan, and we can write 1 over tan as tan to the power minus 1. Using chain rule, we know that the negative in this expression here, that the derivative of tan x is secant of x. We found that in the previous lecture. So here we can rewrite this neatly as this expression here. Now, the negative sign here means that we can rewrite that as cos over sine to the power of 2, and that cosec square on the top will cancel away this cosec square in the denominator. So once you get rid of those cancellations, we're left with negative 1 over sine square, and sine square is nothing but cosec of x. So negative cosec of x square. We can add that to our toolbox there. So let's look at the next example here. So x is multiplied by tan of 2x here. So we can see that we can break this up into a product of x and tan of 2x and use the product rule, and at the same time, so derivative of x is simply 1, the derivative of tan of 2x we need to apply the chain rule here and bring the 2 to the front, and 2 multiplied by secant of 2x. Note that the inside, the input doesn't change, 2x remains as 2x. So here we're going to cross multiply x by 2 secant square of 2x. Applying the product rule here, we'll get this expression, and tidying things up, we end up with that. Now, the next example is arc sine of x. They have told us what the answer is, but we still need to prove what what they've given to us is true. So we can start by writing y is inverse sine of x. That's what that expression means. Arc sine of x is inverse sine of x. So we can take this sine of y equals to x, because I simply applied the sine to both sides. So sine and inverse sine on the right cancel away. So now we can find the derivative of x with respect to y and turn that around. So the derivative of x with respect to y is cos of y. We do need to find dy by dx. So dy by dx is going to be 1 over dx by dy here. Okay? But we don't know what cos of y is. But that's why I've put the right angle triangle here for you. If we were told that sine of y is x, that means that this angle y here is, that y is the angle here. The opposite over over hypotenuse, we can think of x as 1 over x over 1. So x is here, 1 is here. Doing a little bit of Pythagoras, we can know that this adjacent sign is going to be 1 square minus x square. Now that that's the adjacent side. Sorry, I've got the square root of that, so I'm just using Pythagoras there. So reading cosine from the cosine of y from this triangle here is simply the square root of 1 minus x square over 1. So we don't have to write the denominator, we can drop the denominator there. Now we do know what cosine of y is. So this expression 1 over cos of y is basically 1 over square root of 1 minus x squared. Now there is another way of thinking about this. So our final answer for derivative of arc sine is this, but here we also could have used this trigonometric identity, because we know 1 is basically sine square. I'm going to use the angle y plus cos square. And if we had not used this, uh, we could have figured out that subtract sine from both sides. I could have written cos square of y is 1 minus sine square y, and taking square root to both sides, I would have come to the same conclusion that 1 minus sine square of y is cos of y. And looking back at our expression here, substituting x for sine square, I would have come to the same conclusion, that cos of y is square root of 1 minus x squared. Right, so I'm going to the next example. Okay, so I suggest you pause the video here and have a think of how to solve this problem, finding the derivative. This is here, there should be a minus edited the video, so I'm either in the denominator or numerator. Okay, so if you have paused the video and had a go, great. If not, let's have a look at this problem together again. It's very similar to the last example. You can rewrite arc as size and write x is cos of y and take the derivative of x with respect to y. We will have dx by dy equals to negative sine of y. Now in this expression, negative sine of y, uh, we can ignore the negative for the time being. What we are looking for is dy by dx, right? So we do need to invert that expression there. So we can either use the trigonometric identities or that triangle there and think about what it's telling us. This line here is telling us that this angle y, its cos value is x over 1. Okay, there is not a 1 there, but we can think that there is. So what it means is that the adjacent over hypotenuse, adjacent in this right angle triangle, is this bottom sides here, is x, and the hypotenuse is 1. Therefore, the opposite side will be square root of 1 minus x squared. So therefore, the sine of y is square root of 1 over x squared, and because we have a negative sign in front of that, we can take that negative to the top of the fraction and put that there, write it like so. Now it doesn't matter whether the negative is on top of the fraction or bottom of the fraction, but I think it looks neater for it to be on the top. So next example, we're gonna find the arc cos, the derivative of arctan. Okay, so in this example, we are going to find the actually, we have been given the answer to what is the derivative of arctan, and you would have be able to find this answer in the formula booklet, but we still need to show how it's driven. So how do we find the derivative of arctan? So with to the previous examples, we can take the tan of x for both sides and rewrite x equal to tan of y, because arctan and tan are inverse functions and they cancel each other out. So the approaches for the notation there, that's taking two sides. So what we can do is find the derivative of x with respect to y, which is secant squared, and then invert the this fraction because we want to find dy by dx. So we have to, well, we already know that 1 over secant square is simply cos square of y. But what is, there is no y in our answer, everything is in terms of x. So we need to do some around this question or trigonometric identities. If you think about y being equal to sine square of y plus cos square of y, it's not hard to do some rearrangements of this formula, and we get cos square of y being equal to 1 minus sine square of y. And looking at the first line here, sine square, how can we figure out the y's? sine. So the angle here, this in this problem, y, uh, the tan of y is x. So we can think of x as x over 1. So the opposite over adjacent is x over 1. So that tells us the hypotenuse of this triangle is 1 square root of 1 square plus x square. So when we want to find the sine of y will be simply opposite, which is x in this case, over hypotenuse, 1 plus x squared there, right? So, and if we substitute that into this expression, 1 minus sine square is 1 minus x over 1 plus x squared under the square root in the denominator. And we can get a common denominator here and write this as 1 plus x squared, subtracting x here, all over 1 plus x squared there. So, right, so dy by dx is simply cos square of y. But how can we know what is exactly cos square? Well, we can use this triangle that we have over here. We can say if the angle y is there, tan of y means the opposite over adjacent. So the opposite is x and the adjacent is 1. Therefore, the hypotenuse will be 1 square plus x square under the square root. And from there, we can say that cos of y, cos of angle y is simply 1 over the square root of 1 over x squared. Now, we do have cos square here, so when we put that fraction, that denominator, the square root will cancel away with the square on the outside, and we are simply left with 1 over 1 plus x squared. And that's exactly what the answer should have been. Okay, so let's look at another example. So in this example, first of all, we're going to find the derivative of tan to the power of 4 of x. You can think of tan of x raised to the power of 4. And there is a function inside another function, and therefore we can use the chain rule here. To answer part A, we will simply rewrite that with the power rule, and we do know that the derivative of tan of x is secant square. So after using the power rule, 4 tan to the power of 3 needs to be multiplied by the derivative of itself, which is secant square. So we can simplify that as so. So looking at part B, there is y equal to cosecant of 2x over x squared. So there we have a fraction, therefore we're going to take the quotient rule and apply it to this question. So the derivative of the denominator is quite simply 2x, and the derivative of the numerator cosecant of 2x. As in our previous examples, we figured out how to find the derivative of cosecant. If not, you could use the formula booklet, which I've in the bottom of the page. The derivative of cosecant, if you don't remember, is negative cosecant x times by cotan of x. Now that k is a constant that may or may not be 1. In our case, that k is actually a 2. So therefore, we do have to apply the chain rule there and bring out the 2 at the front and write this as negative 2 cosecant of 2x times cotan of 2x. So, and then what we're going to do is make sure we put the right expressions in the right place because we know that v times u dash has to come first on top of the fraction, and then we have to use u times v dash. So once we put the right terms in the right places, we will get this expression here, and we can do some simplifying because I can spot the x common factor here, and also cosecant of 2x is a common factor, so we can factor those first by an x, and then factorizing cosecant of x, negative 2 cosecant of x, we'll get such expression. Okay, so now looking at the question C here, secant raised to the power of 3 means that basically there is one function that you can write as secant to the power of 3 and apply the chain rule here. If you don't remember, secant, its derivative is secant itself multiplied by tan, and so once we apply the power rule, we'll have 3 times secant square, and that needs to be multiplied by the derivative of secant itself, which is secant of x in our case, times by tan of x. Now, you can see that here we have a secant in front of tan, and that secant we can multiply by the secant square and have secant raised to the power 3. So the simplest answer in our case is this. Okay, so let's have a look at this example here. We figured out what's the derivative of arcsine, but here we have x squared as the angle, as the input here for this expression. So we do have to use the chain rule. So we're going to simply say u is x squared, we find the derivative of y with respect to u, and we multiply that by the derivative of u with respect to x. So this expression we figured out in a few minutes ago how it was driven, so I'm simply using that result there, and derivative of x squared is 2x. So once we multiply these two together, as the chain rule suggests, we will have 2 over 1 minus u squared, but we need to replace u squared with x squared. So, well, u itself is x, so x squared, so x squared times raised to another square will give us power of 4 in under the square root. 1 minus x to the power of 4. Alright, so with that, I think we've been through quite a few examples there. So let's see what's next. Okay, so here I've taken question 5 as an example for you, and I've solved it for you. I'm not going to go through the explanation. If you like to pause the video and have a go at question 5, I'll show you that in a second now. The answer is, so you can pause the video and try to verify that for yourself. I'll see you in the next lecture.